Matrix, welcome. It is finally your time to shine on a Monday, and it's Matt's time. I am Looney.
Hi, Looney.
I haven't seen you. I can since last year, probably.
I hope the grade 12s have seen me because I've been here the last couple of Mondays, so it's lovely to see you, and I'm very happy to see the grade 12s again.
What are we doing for the Matrix today?
Today we're doing a really interesting section, which is kind of a follow-on from what the grade 11s were previously doing in the previous lesson, which is similarity. So,
Alright.
yeah.
Mindsetters, we have our genius back in studio with us in DFA. Hello.
Hello, how are you?
I'm good. How are you?
I'm fine.
Do you want to tell the grade 12s where you're from?
Yeah, the grade 12. I'm from Progress Comprehensive High School in Soweto, Pimville.
All right. And DFA is such a genius, guys. He can answer all the questions. We don't even need timeline and studio.
Oh, that's great.
You can
Okay.
take over the lesson if you want. Don't forget to hit us up on Facebook. Mindsetters on facebook.com/LearnExtra. And then our Twitter handle is @LearnExtra. And you can download all the show notes, the videos, and the schedules on learn.mindset.co.za. And if you want to win yourself this awesome Cassia calculator, all you need to do is visit our Facebook page. There is a test yourself link there with a curio code. You click on that link and then you enter the code. You can answer all the questions, fill in all your information, and you'll stand a chance to win this calculator. And you have until Monday at 8 in the morning. So you have all the time in the world. You can watch the show, then maybe do some other stuff, check on your notes, and then you can enter this competition, guys. It's an awesome calculator to have, especially for your exams, for your tests, and everything else in maths. So with that said, Tamerlan.
Right, okay, well, welcome, guys. And today, as I mentioned, we're going to be having a look at similarity, which is very closely linked to your circle geometry. Okay, so everything you guys were doing in the previous lesson, I hope you were all watching, you're going to be using that theory together with the similarity theorems to solve a whole lot of new different things. This section is actually from the previous optional paper 3, which obviously has been, we no longer have that. So these sections have now been reincorporated into our syllabus, and I'm excited about it because I actually think they're really cool sections. Okay, so let's have a look at, just quickly having a look at what we're doing today. So very quickly, we're going to have a look at the conditions for similarity. What is it that we need in order to say that we've got two triangles that are similar? What is similar triangles, okay? We're going to have a very quick look at the similarity theorem, all right? Remember, grade 12s, that a portion of your exam is going to be what you call your bookwork, okay, which is going to be your theorems. You're going to have to learn these because if you actually ask to prove your similarity, your theorem is what you're going to need to do, okay? And then obviously the most important part is solving the similarity riders, so actually applying all that theory into one of these big complicated looking diagrams, okay? Well, hopefully not too complicated, so let's have a look. We've got a nice challenge question for you today. So I want you to take a close look, and then hopefully by the time we've worked through a few examples, you'll be able to actually get this answer right and get it and give us the correct answer over here. If you were watching me last week, all right, you'll remember that I really focused quite a lot on what it was that they give you in the write-up in the beginning of your sum, okay? Have a highlighter in your hand. Make sure you're reading that beginning piece of the information really carefully. If they've mentioned you've got a tangent, or if they've mentioned you've got parallel lines, those are all really important pieces of information that you've got to use when you're solving these sums. So when you're reading, very carefully reading the beginning part over here. So we've said that in the figure, we've got a line VQ, which is a diameter. That's an important piece of information of the circle with center. Oh, there's another important piece of information, guys. It pertains to particular theorems that we need to be able to use, okay? So just remember that. The chord EU is drawn parallel to the tangent, okay? So parallel, we've got a whole lot of theory there: corresponding, co-interior, alternate, and tangents. Well, there's a whole lot of theorems there that we need to use relating to tangents, okay? So to the tangent at the circle at Q, and it cuts VQ at N. The point R lies on the tangent to the circle such that, okay, here's important, RE is perpendicular to QE. Okay, so what you're going to have to do, guys, the first thing is you're going to prove the triangle VNU is similar. The symbol for similar is 3 vertical lines, is like that. Similar to triangle QER, okay, that's the first thing. And once we've done that, we are then going to prove that that EN over VN is equal to ER over EQ. If that looks a little bit strange at the moment, as we work through a couple of examples, you'll actually see exactly how we get to that. So just hang on a few seconds. And then once we've got that, the final question, hence, the word hence is always telling you to obviously use what you've found in the previous questions, and you're going to find the actual length in simplest third form of your distance from, calculate the length of RQ. That's the one we're looking for. All right, guys, so that's your challenge question. As we're working through the questions today, I want you to think about that so that you can actually get that question correct. Okay. Our summary, all right, so let's quickly talk about the conditions for similarity. All right, similarity is we've got two triangles. They're not necessarily equal in size. The one might be smaller than the other, but there are two conditions that make them similar. First condition is that all three angles in each of the triangles have to be exactly the same. All right? So in order to have similarity, the first thing we need to have is angle, 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 proving all three angles equal. The second condition for similarity is that the sides, the lengths of the sides do not necessarily have to be equal, but they must be in proportion. Okay? So the other condition is that our sides are in proportion. All right, and what I mean by that is basically if I've got two triangles, if one side of one triangle is exactly half the length of the corresponding side in the other triangle, then every other side in each of the triangles must then be half the length of the other. So very quickly, if we had a triangle where I had 10, I've got 8, I've got 6, and I've got a much smaller triangle over there, as long as that length is 5, that 4, and that 3, the sides are in proportion, and we can say that they are similar triangles. Okay. All right, guys. What I've then done for you over here, and in fact, I'm going to challenge you to actually download the notes on our website and give this a try. I've given you the theorem, okay, but I've actually left out certain pieces of the theorem, which I'd like you to go back into your notes and see if you can fill in for me, okay? The theorem which is proving your triangle similar. All right, so go onto the website, download those notes, and see if you can actually fill in what the missing parts of that theorem are. Okay, it also helps you to study that theorem. All right. Okay, let's not waste any time. I think let's get straight into a couple of examples and let's see how we manage to actually apply this theory over here. All right, so let's start with this one here. Let's read it carefully. In the diagram below, the chord xy is produced by its own length 2a. All right, there, guys, the value of that statement is that it's saying that your line from x to y to a is all a straight line, so there's no curve or bend in that line. And tangent, okay, so tangent AZ is drawn to touch the circle at Z, okay, so there's our point over there. And XZ is produced to meet the line perpendicular to XA at B. So there's the 90 degrees that they're referring to over there. And AZ, the line AZ is equal to AB. So this line over here is equal to that line over there. All right, so they've given me a bit of information there. Let's see if we can start by finding the first thing. I'll leave it like that. Question 1. Prove that Z3, the angle of Z3, is 90 degrees. So this is my angle of Z3 over here, and I have to prove that it's equal to 90 degrees. Okay. Right, what I'm going to suggest is this. There's no numbers here whatsoever. They haven't given me any angles or sizes of angles. So a good starting point is you need to try and call something x, okay, because it just gives you a value to work with, and you'll find that it actually is very useful, okay? Now, no one's guiding us. No one's telling us where to call anything x. So this is a little bit up to you. You have to figure this one out yourself. But they're helping us a little bit over here because they have told me that I've got AZ and AB equal to each other. So I hope you're remembering that if those two lines were equal to each other, then these two angles would be equal to each other. Okay? So I think that's quite a good place to put our x, because both of those angles would then be equal to x. Okay? So the first statement we're going to make is the following. We're going to say let angle Z1 equal x. Okay, please make note that if you do call something x of yourself, you need to tell your teacher what it is that you're starting with. So please make that statement. Let whatever it is equal x. Therefore, we're going to be able to say that angle B is also equal to x. Okay, and our reason for that is because we have equal angles opposite equal sides. Equal angles opposite equal sides. Okay. Right, what else can I see? I'm trying to get Z3 to equal 90 degrees. Let's see. So I've got that as x over there, that's x over there. All right, I wonder if you guys can see this. I've got a very big triangle here. Big right angle triangle all the way from x to a to b. All right? So if I know that that's 90 and I know that that's x, then do you guys agree that we can work out this angle here because of interior angles of a triangle? So all three angles together would be 180. That's already 90. So 180 minus 90 is 90. And that's already x. So leaving us over here with a 90 minus x. Okay? So angle x is going to be equal to 90 minus x, and that's because they are interior angles of a triangle. And you can actually state it's triangle XAB, of triangle XAB. Okay. Right, now let's see what we've got over here. We have got a tangent. Let's not forget about our tangent. Let's highlight our tangent nicely. They told me that this over here is the tangent, that pink line over there. So let's look at this. If I've got a tangent, do you remember our tan chord theorem? The angle between the tangent and the chord equals the angle in the opposite segment.
Yes.
All right? So that means that you agree with me that angle Z2 is what?
90 minus x.
90 minus x, okay? So Z2 is going to be 90 minus x, and our reason for that, tan chord, okay, which is going to, okay, so I'm sitting with a 90 minus x over here. Are you seeing how we can get Z3?
Yes.
How are we going to get that?
Because we know that, isn't we have a tangent there, and then xz. No, they didn't tell us that they meet at at 90 degrees. So.
Okay, let me point this out to you. What about this? Have a look here. What do those three angles add up to together?
180 degrees.
180. Okay, now we already know that that's x, and we already know that that's 90 minus x. So if I take 180 and I subtract 90 minus x plus x, if we do the sum, what we should land up with is
90 degrees.
Okay, so there we go. So we can say then that angle Z3 is going to be equal to 90 degrees because of adjacent angles on a straight line. Okay, sometimes, guys, it's the obvious things you've got to look out for, so you always got to, and that just comes with practice, okay? All right, so now that we've done that, we've proven that this is 90 degrees, so let's actually fill that in so we remember if they've asked you to prove it, you've got to use it once you've proven it, okay? Okay, now they're saying prove triangle AXZ. So AXZ, which I'm going to have to just highlight as such, is similar to AZY. Let's highlight it in purple. AZY, that's this one over here. Okay, I hope that's clear to everybody. All right, guys, so the way we set out a similarity proof is we have to set it out properly. So I'm just going to scroll up for a minute, and we start off by saying, in triangle AXZ and triangle AZY, okay? In those two triangles, remember, guys, the challenge here is we have to prove similarity, we're either looking for an angle, or we're looking for sides in proportion. Now, obviously, I don't have any lengths of the sides of these triangles, so I'm not going to be looking at that condition. I definitely am looking for angle. And the really nice thing about proving three angles in a triangle equal is that if you manage to prove two of them equal, the third one has to be equal, because if the three angles in a triangle add up to 180 and two of them are already equal, the third will automatically be equal. So in fact, your job is cut down by a third. You only need to actually find two of them equal to each other. Okay, so let's have a look. We're trying to prove this green striped triangle equal to the purple striped triangle, And let's see what we've got. I've got an angle of, I've got a common angle of A over there. All right, what else do we have equal?
Z2 and X.
Z2. Okay, so we've got Z2, this one over here, and this one over here.
Yeah, equal also.
So there we go. That's all we had to use. Hey,
And
so it's
then
quite nice. Hey. All right. So angle A. So we start by saying angle A is equal to angle A in each of the triangles, and my reason for that was common. Okay, common angle. We can say that angle Z2 was equal to angle X. And what we can say there, guys, is that it's proven. We actually already showed that in the previous question, so we can just state that. Okay. Leaving us with the last angle in each of the triangles. In the small purple triangle, this angle of Y is the third angle in the triangle. And in the big green triangle, this whole angle of Z is your big angle. So angle Y is equal to angle Z. And our reason there is it is the third angle in the triangle. Okay. Once we've got that, here's now a really important part of this. We can then say that, therefore, triangle AXZ is similar to triangle, but, okay, what do we have to remember over here? We've got triangle AXZ, and now I need to state the other triangle over here.
Yeah, you need to put them the way they were corresponding.
Exactly.
The angles must correspond.
Such a star. You've got to get it the right. You've got to get it in the right order. Okay, so let's just make sure we've got AXZ and AZY.
Right.
Let's just make sure that that's correct. Angle A was equal to angle A. Angle X was equal to angle Z, and angle Z was equal to angle Y. So yes, we've got that in the correct order. And please don't forget to write that it's angle, angle, angle. Okay. Right, here's my favorite part of these. This looks so tricky. Okay, we've now got to prove that AZ squared is equal to AY times XA. It's so easy.
Yes.
All right, this is what we're going to do. This is what I call my eyebrows and my smile, okay? Because what I'm going to do is I'm going to do a little green eyebrow above the first two values in your first triangle, and I'm going to correspond it with another green little eyebrow over there. Then I'm going to have another eyebrow over the corresponding eyebrow there, and we're going to put a big smile between these two over here. Okay, and that's how you're going to set this up, because remember, guys, if you've proven that the triangles are similar, you have proven that the sides are corresponding. They're in proportion. So therefore, here's our statement. AX over AZ is equal to XZ over ZY, which is equal to AZ over AY. And let's see, we're looking for an AZ squared. So what I want you to do is this. Look for AZ. I've got an AZ there, give it a tick. And I've got an AZ over there, give it a tick. And AY and X. So AY and XA, look there, they're all together. So what we do is we cross multiply. So AX times AY. And AZ times AZ is AZ squared, and we did that by means of cross multiplication. Okay, so there we go, guys. If you're looking at that third part, generally, once you've proved similarity, it's a very easy little path to get to that final part over there. I'm sure you need a break. Let's take a short break, and I'll do some more examples with you after that.
All right, mindsetters are going to take a very quick break, but quick congratulations goes out to Tupang Masimula. You have won yourself this Casio calculator. Congratulations to you. Mindsetters, if you want to be like Tupang, go to Facebook. There's a test yourself link there. You click on that link, and you'll stand a chance to win this awesome calculator. With that said, let's take a very quick break, and we'll see you straight after this. Welcome back, guys, from that break. I hope you're still enjoying the maths lesson. I'm not going to waste your time.
Let's get going. Right, guys, so let's have a look at another example. Not involving circle geometry, but still involving similarity. So let's see how we go with this one. Triangle PQR and PST are right angled triangles. They've told us that RQ, so the distance from R to Q, is equal to the distance from S to P, and they are both equal to twice the length from R to S. Okay, all right. S is a point on RP with ST perpendicular to PQ. All right, so we can see the little 90 degrees that's been drawn there. The first thing they're asking of us is to write down without a proof. Okay, so we don't need to do the whole proof of angle, angle, angle. They're simply asking us to state it, a pair of triangles that are similar. All right. Well, which two triangles would be similar over here? I've got the big triangle of QRP. Okay.
STP.
And absolutely. Then we've got this little triangle of STP. And why would they be similar?
Because the angle at T is equal to the angle at R, which are both equals to 90.
Both of those are 90.
And then angle at P is also equal to the angle at Q.
Fantastic. And what do we call that?
Base angles of isosceles.
Okay, it's not an isosceles triangle at this
That
point.
one.
We're going to call this
The
common.
big one.
Oh, the big one.
P and
Okay,
Q.
just be careful. That's only SP. SP is equal to QR.
Oh, I thought the whole thing.
No, it's not the whole one. So that's just that little piece over there. Okay. So what I want you to tell me is that this angle P is common. Okay, it's common. So therefore, it's going to leave us with this our last angle of S being equal to that last angle of Q being the third angle in the triangle. Okay.
Yes, yes.
All right, guys. So therefore, all they're wanting us to do is state the similar triangles. Remember, what's important is we have to get the order correct. Okay. So if I state that triangle QRP is similar to triangle, then I need to get the corresponding angles matching. Angle Q in the green triangle was equal to angle S in the purple triangle. So there's starting with S over there. Angle R in the green was equal to T in the purple, and P in the green was equal to P in the purple. So that's a very important thing, grade 12s. You must get that order correct, because once you do your eyebrows and your smile, and once you match those corresponding sides, if you don't have them in order, you're going to land up with a problem. Okay. All right, now they've asked for something interesting. Show that ST is equal to 2 over root 13 times QR. Have you had any luck with that?
Yes, I think here we're going to just use proportionality of the sides.
Okay, and that's a really good start. Okay,
Yes.
so grade 12s, once you have proven similarity, if you asked to prove a question such as this, and you may be a little bit unsure as to where to start, the best place to start is put the sides of your triangles in proportion. Okay, so that's where we're going to start. I'm going to put QR over ST. I'm going to put RP over TP, and I am going to put QP over SP. Okay, let's write them over here. So QR over ST is equal to RP over TP, which is equal to QP over SP. And in fact, we do need to state a reason for that. We can't just randomly say that without actually giving it a reason. So therefore, the reason we need to state is that sides of similar triangles in proportion. In proportion. Okay. Okay, so now that you've got that, let's see. We have to somehow find a root 13 in here, which might be a little bit challenging. So let's see if we can figure this out. As it stands, I've got 0 lengths. So no one's told me anything about length. So once again, we have to kind of come up with something for ourselves here, okay? We have been told that QR is equal to SP. So what about if we call it X? Let's give ourselves X as a length over there. So that's X over there, and that's X over there. You happy with that? Okay, so therefore, we know that the length from R to S is exactly half the length of SP and QR.
Yes.
I'm going to suggest something. Instead of working with a half X, maybe let's do this. As long as they're the same, it's okay for us to do that. If each of those lengths were 2X, then we would be able to call that just X over there. Makes it a little bit nicer to work with. Okay. All right, so we've got that over there. So let's fill in a few things. The length from Q to R. Do we know the length from Q to R? Yes, I do. From S to T, no, I don't know that yet. RP, my distance from R, what would the distance from R to P then be? All the way along?
R to P.
In terms of X, obviously, I've got a 2X and I've got an X.
3x.
So it's going to be 3x. So the total length of R to P is going to be 3x. So we've got that. We don't have TP. QP. Right, QP is an interesting one. Are we able to actually work out the length from Q to P?
Yes, Pythagoras.
Pythag, absolutely. My length from Q to P squared is going to be equal to QR squared, which is 2x,
X squared.
plus the distance from R to P squared, which we know is 3x.
3x squared.
Okay, so that's giving us 4x squared plus 9x squared, which is giving us, and haha, this is where this 13 is coming from, 13x squared. Okay, but don't forget that it's QP squared. We don't want QP squared, we just want QP.
Which is
So we're going to take the root of 13, and then x squared would become just x. Okay. Okay, so, all right, we're starting to piece this together because I can now see where that root 13 is fitting into the whole story. So let's fill in what we have. We know that the distance from Q to R was 2x. I'm just going to write it over here, grade 12. So I've got 2x as the distance from Q to R. From S to T, we unfortunately don't know that, so I'm going to leave it as ST. RP, we're looking for RP, which we said was 3x. From T to P, no, we don't know that, so we're going to have to leave it as such. QP, Q to P was, that was our answer of root 13x. And SP, my distance from S to P was 2x. Okay, so this is what we're going to have to work with. I'm looking for a QR. QR. Let me just double check something. Where did that go to? SP. No. Okay, QRST. All right, so we're going to have to look at this over here. Am I correct in saying QR is 2x? Somewhere I've done. Because what we would have to do then, now guys, is we'd have to cross multiply. So I'd have to say, let me just see here. I would have to say, no, something's wrong here. Sorry guys, I need to just double check this and see where.
QR is not 2x.
Hey, is it not? Have
Yes.
I? Okay, find me my mistake. Where have I gone wrong?
Because
You said QR is not 2x. Okay, so it's just QR.
yes.
Okay, all right, sorry. So then that fixes it. So if I cross multiply now, I'm going to have 2x times by QR, which is equal to root 13x times by ST. Okay, and to get ST on its own, I would just divide the root 13x on the other side. So therefore I would have 2x over root 13x
Times QR.
times by the QR, which is equal to the ST. My x's will cancel nicely, and there we go. So we've got our 2 root 13, 2 over root 13 times by QR, and that got us our ST. Okay.
Yes.
See, we make a great team. All right, there we go. All right, guys. So a good lesson over there is that if you're having to find a value, as I did in the previous example as well, letting something equal x is often a good starting point. It's a good helping hand in kind of finding a pathway through the sum. So it's an option if you're feeling like you needing to have something to work with. All right. Okay. Let's have a look at another one. All right, this time we've got a semicircle. When figure AGDE is a semicircle. So obviously what we know about that is that we most definitely have a diameter. Okay, the diameter is AE. And there's a couple of interesting things about a diameter. We have radii, and we also know that a diameter subtends an angle of 90 degrees. Okay. AC is the tangent. Okay, that's always interesting. Tangent to the semicircle at A, and EG is produced intersects AC at B. AD intersects BE and F. Okay, those are all just giving us details of the rider. AG is equal to GD. Okay, here they've actually filled it in for us, so they were nice. That was equal to that. And E1 is equal to X. So this one was a little bit more helpful. They actually gave us an X to start with instead of leaving us to figure it out ourselves. First thing they're asking of us is to write down, with reasons, 4 other angles which is equal to X. Okay, so let's see. What can we see over here?
E2.
B, which one, love?
E2.
E2.
E2. The one down there.
This one here?
E. E.
Where's E? Oh, this one here. Sorry.
Yes.
Okay, and give me the reason as to why.
Subtended by equal chords.
Okay, so absolutely. Okay, so this chord, that's a great reason. Well done. That chord over there, GD, is equal to the chord of GA. And equal chords subtend equal angles. Well done. So that's our first one. Let's say E2 is equal to X. Equal chords subtend equal angles. Okay, so we've got an X over here. Perfect. I can see another one. I can see that D2 is then going to be X. All right. That's going to be angles in the same segment. Angles in same segment. Okay, so we've got an X over there. Where else do we see an X?
A2.
A2. Okay, A2 is going to be equal to X. That over there is equal angles opposite equal sides. Opposites equal sides.
A3.
And finally A3.
Yes, A3.
Okay. Sorry, E3. D3.
There's A.
This one here?
Yes.
Okay, and why is that one equal to X?
Tan chord.
Okay, let's double check. Let's make sure. Tan chord, I'm happy with that. It's tan chord. Okay, so that's equal to X tan chord. Cool. All right, so all of those, so we've got X's in all of these little angles over here. All right, and obviously the fact that they've asked you to prove all of those angles for X, we're definitely probably going to be using them in the second part. So let's see what they want from us here. Prove that BE times DE is equal to AE times FE. Okay, now this kind of question kind of follows on, or normally follows on, from a proof of similarity. Okay, so they've been a little bit nasty here in the fact that they're asking you straight away to find this combination of sides before even asking you to find, or without having asked you to find similarity. But the point is that you need to know that in order to find that combination of sides, you need to prove similarity first. Okay, so looking at the sides that they're wanting you to find the combination of, you need to determine what triangles we're going to be working in. I'm looking for a length of BE, all right? So a distance from B to E. I'm looking for DE, which is this one over here. And I'm looking for AE, so we now are down here. Let's change to orange. And we're looking for FE, which is over here. So I think it's pretty clear as to which triangles we're having to prove similar. Okay. All right.
Yes.
Sorry, BE. No, sorry. Let's erase. That's not the one we're looking for there. We want this side. We wanted BE, so it's going to have to be that big triangle. Am I right? Triangle BE, so let's just double check again, from B to E, D to E, A to E, and F
To E.
to E. Okay,
Yes.
all right, that BE. Okay, let's have a look and see. All right, so we have now got to prove similarity. So we're going to start by saying in triangle, all right, in triangle AFE, and triangle BCE. Okay, can we prove them similar? Do we have a similarity here? We've got an X equal to an X. And what else do we have? I think what I'm going to do, okay, well, hang on, let's just think about this here. We had a diameter. So we've got a 90 degrees over there. We've got a 90 degrees over here. We have got, from BT, what else do we have? We've got a tangent perpendicular to a radius, so that would be 90 degrees over there. I think what I'm going to do is, do we have time to have a short break? I'm going to have a look at it. I'm going to let the learners have a look at it. Let's see if we can get the right triangles before we carry on.
All right. Mindsetters, let's take a very quick break and we'll see you straight after this. Welcome back, Mindsetters, from that break.
Okay. All right. Tamlin just had to relook at that quickly. But we've actually figured I was looking at the wrong triangles, which I pretty much suspected. But what we need to actually be looking at is triangle BAE and DFE. Okay, those are the two triangles that we needed, which I'm sure you guys figured out already. And let's see. So in triangle BAE, and our triangle DFE. Okay, so we know that we had a 90 degrees, which we happened to mention before we went on our break, that angle D3 is 90 degrees because angle's in a semicircle.
Yes.
Then we can actually say that angle A, that whole of angle A, is going to be 90 degrees over there, because if we had a circle center, which would give us, we know that AE is the diameter,
yes.
so therefore a radius
And
and
a
a tangent
tangent.
are perpendicular. Okay, so let's set this out properly. So D3 is 90, angle in semicircle. Angle A is 90 because of tangent perpendicular to radius. Okay, so that obviously means that angle D3 is equal to angle A. So D3
Third angle.
is equal to angle A. Which other angles are equal? Okay, so we proved earlier that this one over here is x and that one over there is x, so that's easy. E1 is equal to E2. E1 is equal to E2, and we can say proven. Which leaves us with the third angle in each triangle going to be, okay, now obviously we just make sure you get them in order. If I'm working with triangle BAE first, that's the one we have to state first. So therefore this angle of B is the third angle in that triangle. So angle B is going to be equal to the third angle in the other triangle, which is this one over here, F2. Okay. F2, third angle in triangle. Okay, and by stating them similar, so that means that therefore triangle BAE is similar to, remember angle B was equal to angle F, angle A was equal to angle D, and angle E was equal to E. So therefore it's going to be FDE.
FDE.
Angle, angle. And from there we use our proportional side. So we've therefore got our side of BA over FD. That's equal to AE over DE. AE over DE. And BE over FE. Reason sides of similar triangles in proportion. Okay. And remember what we're looking for? We're looking for a combination of BE times DE. BE times DE. And we're looking for an AE times FE. AE times FE. So that's great. It's just a straight cross multiplication between those terms over there. So AE times by FE, and that was equal to BE times by DE, and that was what we were looking for. All right. How are you finding these? Pretty
Yes,
easy.
this is very easy.
Okay, great. Okay, guys, I hope you at home are finding these easy too. And if you're ready to have another look at another example, let's move on. Okay. All right, so another example we've got over here. This is a nice, interesting one because we've got two triangles that are intersecting each other over here. Let's see what we've got. They're telling us that O is the center of circle CAKB. So CAKB, that's the smaller of the two triangles, and O is the center of that. AK produced to intersect at circle AOBT, which is obviously your bigger circle at T. And they are telling us that angle ACB is X. Okay, so again, they've been nice enough to actually guide us here and tell us which angle they want us to call X. It just helps. Sometimes they do, sometimes they don't. Okay, so just be aware of that. The first thing we are looking for is to prove that angle T, here's angle T sitting over here, is 180 degrees minus 2x. Okay, so let's see, what can we do? I can see that in my smaller triangle, or not in my smaller circle, if that angle over there was x, all right, then they told me that angle O was at the center of the circle, which means that angle O would have to be 2x. Okay, it's double. So we're going to say that angle O, let's call it angle AOB so we're clear exactly where it is. AOB is equal to 2x. Angle at center is equal to 2 times angle at circumference. Okay. So now that I know that that's 2x, let's move our attention into the other circle over here. If we look carefully at it, what do we see? I hope what you notice is that we actually are sitting with a cyclic quad.
Yes.
Okay, there's a cyclic quad over there of OBTA. Okay, and the opposite angles of our cyclic quad we know are supplementary. So angle T
It's going to be 180
would be 180 minus 2x. Excellent. Okay, opposite angles of cyclic quad. Ooh, cyclic quad. Okay, so I'm just going to do an arrow to it. It's a bit small to fill it in over there, so let's just write it on the side. 180 minus 2x. Okay. All right, so that was a nice simple one. Let's see what the next part is. They're wanting us to prove that AC, so this line of AC, they're wanting us to prove parallel to, it's KB. Sorry, that for some reason is not there. But KB is the line that we're wanting. Let me use a different color so that it's more clear. So AC parallel to KB. All right? So proving parallel lines means we need to go back to our geometry theory, which involves corresponding angles, alternate angles, and co-interior angles. Okay, so if I can find any one of those, I then have I've found what I'm needing. All right. So let's see what is there potentially that I could do over here. We're trying to get these two lines, which are green, to be parallel. What I can see is that I've potentially got a corresponding. Okay, potentially if I've got x over here, if I could get B4 to be an x, then we've managed to find corresponding angles. So I think that's a pretty good starting point. Do you agree?
Yes.
Okay, let's see. In our smaller circle, we've got another cyclic quad. We've got a cyclic quad of CAKB.
Yes.
All right, and K1 is the exterior angle of that cyclic quad.
Equals to x.
Okay, so K1 is going to be equal to x because it's the exterior angle of the cyclic quad. Okay. And if we know that, if I know that this little angle over here is x and I know that this one over here is 180 minus 2x, well, let's use our interior angles of a triangle. All right. 180 minus, I'm going to do the sum up here so that I don't squash my working out. 180 minus the angle of 180 minus 2x plus the other angle of x. And what do we land up with, guys? Just x. 180 minus 180 cancels. Negative 2, remember that the negative distributes, so it becomes positive 2x minus x, which is going to leave us with just x. So angle B4 4 is going to be equal to x because it's interior angles of triangle, which means that we can reach the conclusion that AC is parallel to BK. And reason being because the corresponding angles are equal. All right, and that's why we can now state that these two lines are parallel. All right. Okay, so that was a nice one, getting that to be parallel. Now let's see what else we have to do. Sorry, let's move that up a bit. Again, proving similarity. So prove triangle BKT is similar to triangle CAT. So BKT, so it's this little one, that little one down there, and CAT is the big one. Let's see if we can find, we haven't used blue yet. So we're trying to prove this little one over here similar to this big one over here. Okay, so I think first of all it's pretty obvious that angle T is common. What else do we have?
K1.
We've got K1 is X,
And
we've got
C.
angle C, which is X, which means that by third angle in a triangle, angle B4 would be equal to the whole of angle A. All right. Having proven that, okay, so I want you guys, I'm not going to do it on the board just in terms of space, but obviously the proof needs to be set out properly. So you do need to state in triangle, BKT and triangle CAT, and you set it out properly. Angle B was equal to angle A, third angle in your triangle. Angle T was equal to angle T common, and angle C was equal to K1, and we can say proven. We already knew that they were both equal to X. So that as a result, and finally state that it is similar because of angle, angle, angle. Once two triangles are proven similar, always, as a default thing, go to putting your sides in proportion, okay? So BKT, so a triangle BKT was similar to, let's just make sure they had that in order. Angle B was equal to A. Angle K was equal to C. And T was equal to T. That's right, eh? So let me just make sure. B was equal to A. Yeah. Okay. So that's over there. All right. And we're now going to put the sides of the triangle in proportion. So we've got BK over AC. That's equal to KT over CT. That's equal to BT over AT. And from there, obviously, you're going to use the ratio of the sides to find the last question, which, Looney, just to check, do we have time to do the challenge question?
Yes, you can do it.
Okay, so let me finish off this one over here quickly. Guys, just watch out if it's written as a ratio, it's better to actually change it to write it as a fraction.
Yes.
So you would be looking for AK over KT, which is equal to 5 over 2, all right? And that would then you'd find the ratios that match, and you would find your answer, okay? So, so you guys can give that one a try. And what I want to do now, just so that we've got enough time, is to just give you the answer to your challenge question, okay? All right, I hope by now you've had a good look at it, and I hope that you've actually managed to figure it out. Pretty similar to what we've actually been looking at so far, so let's have a quick look and see. All right, so we knew that VQ is the diameter of the circle. We know that it's got a center at O, all right? So VQ, here's our circle center. The chord EU is drawn and it's parallel. They've filled that in first, that EU is parallel to the length of RQ. And they've told us where it cuts and so on. And then the point R lies on the tangent to the circle such that RE is perpendicular to QE. Okay, so we've got a little 90 degrees over here. All right, the first thing they wanted us to do was to prove the triangle VNU. So VNU was similar to QER. Okay. All right, so let's see how we go. In triangle VNU and triangle QER. All right. What have we got over here? What can we say? Have we got anything that's equal at this point? What can you see?
I can see that angle E3 is equal to Q1.
E3, I'm just going to call it X, is equal to Q1, and that's because of alternate angles, hey?
Yes.
Okay. And we could also say then that E3 is equal to angle V because they're angles in the same segment.
Yes.
Okay. What else can we say? We've got parallel lines. Here's something interesting. We can say that this over here from Q to O is a radius. And a radius and a tangent are perpendicular to each other. All right? And because these lines are parallel, we've got co-interior angles. So that would also be 90 degrees because of co-interior. Vertically opposite would make that 90 degrees, giving us Q1 equal to V, 90 degrees equal to 90 degrees, and those are our third angle in the triangle. Okay. That would allow us to prove similarity. Guys, from there, you're going to use your sides in proportion to get your EN over VN equals ER over EQ, and the rest is substitution. So that rest part is pretty straightforward once you've got the sides in proportion. So I hope that that all makes sense to you. What I suggest is go and download the notes because the answers are there. You can double check that they're all correct, and I hope that you all understood that.
All right. Thank you so much, Tamerlan, for the great lesson. Dife, this is for you, man. To say thank you so much for joining us. And I hear you want to do accounting next year to UJ.
Yes.
So this is for you. You can come get it. Come, quickly.
Wow.
Run! This is for you.
you.
Thank you so much for joining us and for being so awesome.
Thank
Mindset is at home. Thank you so much for tuning in. We love you very much. And until next time, guys, if we didn't get through any of your questions, actually, I'll keep Ndife, like, after the show. We'll go through the questions together, and he'll answer you because he's such a genius. But from us, until next time, thank you so much for tuning in. And if we don't get through any of your questions with Ndife, you can send your questions to the learn.mindset.co.za/helpdesk website, and we will answer you there. Thank you so much, guys, for tuning in. We love you very much. Goodbye.